So hello everyone, today we're going to quantize the electromagnetic field. So we're going to consider non-relativistic systems. So here it is appropriate to use the Coulomb gauge. In other words, we will set the vector potential to be divergenceless. So the divergence of A is 0, okay? So this is the so-called Coulomb gauge. If we're working with relativistic systems, then the Lorentz gauge would be more appropriate. So in this gauge, the electric field is defined by Faraday's law to be minus the derivative of the vector potential with respect to time, while the magnetic field is just the curl of A. Now, if we plug these into the Ampere-Maxwell law, then this is a very easy exercise. It's pretty much this equivalent to deriving the wave equation from Maxwell's equations, and eventually you will find that the Laplacian of A is equal to 1 over c squared times the second derivative of A with respect to time. So this is just the classical wave equation. So if we consider a box of length L, and shown here, then of length L, so volume V equals L cubed, then applying periodic boundary conditions, I will get a series of electromagnetic waves. And so here is one wave, and then I might get another one as such, and finally maybe another one like this. And so I will get all these waves, and I can decompose the vector potential into waves of wave number k, and I will have waves going to the right and waves going to the left. So I can write this as ak plus e to the I omega k t, where omega k is defined as usual to be c times the magnitude of k. So omega k is equal to c times the magnitude of k. Plus ak minus e to the minus omega k t. Okay, so this defines a wave traveling to the right, so in the positive k direction, while this defines a wave traveling to the left in the minus k direction. And of course, we have to multiply this by the real space factor e to the I kr. Let me rewrite this in a different way. We'll have to do some manipulation. So I'll write this as A plus minus k. So what I'm doing is, here I'm summing from positive, from some k, let's say from minus k to k, and here I will reverse the order of summation. And so by doing so, I will get e to the minus I k dot r, right? Why? Because this k becomes minus k by reversing the order of summation, minus omega kt, right? Because I need this to be positive, so minus times minus. Okay, so I've reversed the order of summation for the wave going to the left, but I will not reverse it for the wave going to the right. So I will get plus ak minus e to the I k dot r minus omega kt. Okay? Now, note that the vector potential has to be a real quantity. It cannot be a complex valued function. So we need A to be equal to A dot. In other words, the sum over k of A plus minus k star, so the complex conjugate of e to the I k r minus omega kt plus ak minus, again complex conjugate, e to the minus I k dot r minus omega kt, right? This, so I taken the complex conjugate of the vector potential, must be equal to this. So these two must be equal. Because this term right here and this term right here of the waves going to the left and to the right have to be orthogonal, I find that A minus k dot plus complex conjugate must be equal to the factor of e to the I kr minus omega t in the above expression. So it must be equal to A k minus due to the orthogonality of these exponentials. Or alternatively, A to the minus k plus is equal to ak minus complex conjugate. And I can just insert this back into here, and I find that how do I move? Oh, there it is. And I find that A is equal to sum over k of A to the k minus complex conjugate e to the minus I k dot r minus omega kt plus a k minus e to the I k dot r minus omega kt. As you can see, this has to be a real quantity because this is just a complex conjugate of this, right? So this is the complex conjugate of this. This travels to the right and this to the left. Okay, now finally recall that an electromagnetic wave can have two different types of polarizations. It can be polarized perpendicular or parallel to the plane, and consequently, if I can write A, K, these have to be vectors. Absolutely, these are all vectors. So A, K must be equal to a scalar AK times a polarization, and this will add an extra index, okay? And this polarization vector it runs from lambda equal to 1 and lambda equal to 2. So it can take two different values corresponding to the two different polarizations of an electromagnetic wave. Okay? So this is equal to A k minus e to the I k dot r minus omega kt plus a k. Now, just for the sake of simplicity, I will drop this minus sign. I mean, it's not a minus sign, it's minus symbol because it's useless. And I will get this. All of this multiplied by a polarization vector, so we will have to add the lambda index here. There you go. So that's our vector potential. Quite a lot of hard work to get such a simple thing, and someone with good physical insight would probably be able to just guess this, but it's good to derive it more formally. All right, so really this is decomposing the vector potential into waves of wave vector k, and for each wave vector, a wave polarization E lambda, where lambda runs from 1 to 2. Because these are plane waves, k over k, right, E1 and E2 must form an orthonormal basis. Okay? So that's a point that we'll have to keep in mind later on. Wonderful. Now, we have found the vector potential. This allows us to find the Hamiltonian of the system. The classical Hamiltonian of an electromagnetic field is this integral over space. It's E0 times magnitude of the E field squared plus 1 over mu 0, the magnitude of the magnetic field squared, integrated over space. We're working in a vacuum, so there's no dielectrics, no materials, so we can use these values for the permittivities and permeabilities. Okay, but now we can use the definitions of the electromagnetic fields in the Coulomb gauge, which we have right here. Okay, quite easy to remember. And so here we get that this is equal to E0 times the derivative of the vector potential squared plus 1 over mu 0 times the curl of A squared dr. Okay. Now, there are many ways to evaluate these two integrals. They're a bit nasty. You could just integrate it directly, substitute, find the derivative, find the curl of this, and integrate. It is a bit long, and there's a cute little trick which the book Bruce and Flensburg, many-body physics, recommends. And that method is to use Parseval's theorem. So this is a bit of Fourier analysis. I will not prove the result, but essentially Parseval's theorem states that if I take some integral of some function in real space, and this function is actually the modulus squared of f of some other function, right? So if I take this integral right here, then I can write this in Fourier space as the sum of the modulus squared of the Fourier transform. Okay, here I'm using the sum because k is a discrete variable. If it was continuous, I'd have to use an integral. Okay, so it seems quite intuitive. And we'll use this because it allows us to write this integral as a sum rather than an integral, which is usually easier to deal with. Okay, so our first goal will be to find the Fourier transform of the electric field. Now, I'll do the Fourier transform, I'll do it in the variable k prime, because there's going to be a lot of k's flying around. So I'll do it in the variable k prime. And this is quite simple to see. I'll pull up the vector potential. So it's just going to be I omega. This comes from taking the derivative, right? So once you have taken the derivative, all you have to see is you have to look at the components with k positive and components with k negative, and that's how you get a Fourier transform. So this will be ak lambda e to the minus I omega kt times delta k prime. This comes from taking the Fourier transform of e to the ikr. Okay, and this is minus, plus a k lambda complex conjugate e to the I omega kt delta minus k prime. Minus because here we have a minus, and so when we do the integral, the delta function gets k minus k prime. Okay, times e lambda. Now a bit of notation. This is a Dirac delta function, so this is really just equal to this right here. Okay, I won't write this version, it's a bit longer and it won't fit, but these are defined to be equivalent. Okay, so it's a Dirac delta function which only chooses the k vector which is equal to the k prime vector or the minus k prime vector. Okay, this is a Fourier transform of this time derivative. We can also find the Fourier transform of the curl in a completely similar way. So we get sum over k lambda of I k cross product e lambda, right? This comes from how you take the Fourier transform of the curl. And then the same thing, exactly the same thing. Okay. So these are the two Fourier transforms, and now we're actually ready to calculate integrals. Just two quick things to note. Actually, no, we'll note them later. So first of all, the integral of this, which is one of the integrals we were interested in, as you can see right here, by Parseval's theorem, will be equal to the sum over k prime of the Fourier transform in k prime of delta a, of the derivative of the vector potential with respect to time, and we'll have to take the modulus squared. Okay, so how we can write this using this Fourier transform we found. So it will be equal to the sum over k prime lambda prime. Remember, when you're taking the product of two sums, make sure you use different indices, because if you use the same index, it can cause a lot of confusion. Okay, so I will get I omega times the complex conjugate, so minus I omega. Then I will get this whole thing, hoping I can copy it somehow. There we go. Okay, now this will be with E lambda, then dot, right, because we're taking the This will be a vector quantity, so we'll have to take the dot product with its complex conjugate, which we're doing right now. And we will get, right, this is what we'll get, but we'll have to take the complex conjugate. So this becomes a plus, and this becomes a minus, okay? Times E lambda prime, and yeah, so this gets lambda prime, this gets lambda prime, okay, yeah. Next, we use this following identity, so E lambda dot E lambda prime is equal to delta lambda lambda prime, okay? Why? Because as we said, lambda and lambda prime and k form an orthonormal basis. We're considering transverse waves, so these form an orthonormal basis, and orthonormal bases satisfy this rule right there. So in other words, this will reduce to a sum where the lambda and the lambda prime variables are equal to each other. So k prime lambda of omega squared. Now remember, when we're summing over k and k prime, the delta k prime and the delta k prime with minus sign, right? All terms of this product will have to cancel out because one is 0 unless k is equal to k prime, and the other is 0 unless k is equal to minus k prime. And clearly the only vector satisfying this is the 0 vector, and the wave vector that is the 0 vector is not very interesting. So for all physical cases, the cross terms, so such as this one multiplied by this one, will cancel out because the delta functions are not appropriate. However, the terms such as this times this or this times this will not cancel out because the delta functions contain the same variables. In other words, I will get a k lambda squared plus a k lambda squared. So this is equal to, and again, I have lost the sum over k prime when doing this, when simplifying the delta functions. So I end up with this sum right here. 2 sum omega k squared. I forgot the k right here, times a k lambda squared. Great. Now the calculation for the other integral with the curl of the vector potential is quite similar. So I find that the integral of this squared would be equal to the sum over k prime of the Fourier transform of k prime, of the Fourier transform in k prime of the curl squared. Now again, this will be a vector quantity, so we'll have to take the dot product of the Fourier transform and its complex conjugate. So I will have to take this term right here. Okay, this will be equal to this dot with another sum, which will be I k times E lambda prime with a minus because we're taking the complex conjugate, AK lambda prime, sorry, AK lambda complex conjugate plus I omega kt delta k prime plus A k lambda prime e to the minus I omega kt delta minus k prime. Now, here is where we use another identity, and this can be proven quite easily using Levis-Vita tensors, for example, and it's the following. So I'm taking the dot product of these two cross products involving orthonormal vectors, and as you might guess, this is equal to k squared delta lambda lambda prime. This simplifies a bit because our sum will now turn into a sum in k prime and lambda, because when we sum over lambda prime, only the term equal to a given lambda will be the ones that survive. So this is equal to k squared times the product right here, and there we go. And again, the only terms that survive are the like terms where the delta functions contain the same variable. So, for example, these two and these two. And again, we end up with, when we sum over all the k primes, the only ones that survive are the ones corresponding to a given k. So we get the sum over k and lambda of k squared times a k lambda squared plus a k lambda squared. Okay, so this is equal to, now here we can use another identity, which is this one, and this allows us to write this whole thing as sum over k lambda of omega k squared over c squared times 2 modulus of ak lambda squared. We're pretty much done. We've evaluated the nasty integrals which were shown here. So the Hamiltonian really just boils down to this: 1/2 times E0 to sum over k and lambda omega k squared a k lambda squared plus 1 over mu 0 sum over k and lambda of omega k squared over c squared a k and lambda squared. Okay, this is just a bit of algebra. You can work with the wave frequencies and the wave velocities, and you really will just end up with 2 E0 sum over k and lambda of omega k squared a k lambda squared. This is the classical Hamiltonian. Now I can write this in yet another way by introducing the real and imaginary parts of the A amplitudes. So I can say A k lambda is equal to A k lambda real part plus AI A k lambda imaginary part. And if you do this, you will get omega k squared A k lambda real plus A k lambda imaginary squared. Now this is starting to resemble more and more the Hamiltonian of a harmonic oscillator. Why? Because it contains two quadratic terms. This omega k squared is hinting at some sort of angular frequency of an oscillator. And indeed, one can very easily prove that there are two sets of conjugate variables, right? So one is the following: kq lambda equal to 2 square root of E0 AR k lambda, and pk lambda equal to 2 omega k square root of E0 AI k and lambda. Now these are canonically conjugate variables. What this means is that if I take the Hamiltonian, if I take its derivative with respect to q, for example, and I'll add the subscripts, then I will get the other variable with some sign change. So I get the time derivative of the other variable with some sign change. Same thing here. And you can check that given these two definitions, this is what happens. Okay, so if we use these two variables to rewrite the Hamiltonian, then essentially this will turn into 1/2 square root, sum over k and lambda of pk lambda squared plus omega k squared qk lambda squared, which, believe it or not, is the Hamiltonian of a harmonic oscillator. So we've shown that in the classical picture of physics, this is a harmonic oscillator. So now we can quantize it and get a quantum harmonic oscillator. And we do this in a very similar way to how we quantize the normal harmonic oscillator. And that's essentially by promoting these canonically conjugate variables to canonically conjugate operators. So I can just upgrade this p and this q. So this p q lambda will become an operator. Same with the q. And because they're canonically conjugate in the classical picture, we know that they must satisfy in the quantum picture the canonical commutation relations. So this must be equal to I h delta k k prime delta lambda lambda prime, and etc. You know what the canonical commutation are. Okay, so this Hamiltonian becomes Hamiltonian operator equal to 1/2 sum over k lambda of p k lambda squared plus omega k squared q k lambda squared. Okay, so we've quantized it, and now we just use the typical tricks of the ladder operators. I can introduce the ladder operator a k lambda equal to square root of h bar over 2 omega k times omega k qk lambda minus, plus I p k lambda, and I can define its Hermitian conjugate as well in a very analogous way. So square root of h bar over 2 omega k q k lambda minus I p k lambda. So these are ladder operators. I can actually use these to express my initial operators. In other words, I can write q k lambda as just square root of h bar over 2 omega k times a dagger k lambda plus a k lambda. And similarly, I can express the momentum operator as I square root of h bar omega k over 2 times a dagger k lambda minus a k lambda. Okay, so I've introduced these ladder operators defined using the canonical momentum and canonical position and momentum operators. So if I plug these into here, it should give me a new Hamiltonian, and it's quite easy to evaluate. For example, qk lambda squared, well, what will that be? That will just be h bar over 2 omega k times alpha, a k lambda dagger squared plus a k lambda squared plus a k lambda dagger a k lambda plus a k lambda a k lambda dagger. And in a very similar way, I can also find p k squared. I'll leave that as an exercise, so this is just example. Okay, but if I plug these into here, do some algebra, I will end up with a new Hamiltonian given by the very familiar expression k lambda a dagger k lambda a k lambda plus 1/2. There you go. We've essentially quantized the classical Hamiltonian of electromagnetic radiation, and we've quantized it to a harmonic oscillator. We're really done here. There's not much else to do. One last thing that we might want to do is write the vector potential using these creation operators, these ladder operators. This is very easy to do because I defined a k lambda r to be equal to q k lambda over 2 square root of epsilon 0, and also a k lambda I to be equal to, oh sorry, no, these are classical, but when I quantize the Hamiltonian, I turn this into an operator. So this amplitude now turns into an operator. So similarly, this imaginary part is the momentum operator over 2 omega k square root of E0. So if I plug these in, these expressions into my original expression of the potential of the vector potential, right? So if I plug them into here, then I will finally get another expression for the vector potential, which you can find in the lecture notes. It's quite long, and this is quite a long video as well. But you'll find in the lecture notes, and but it's really just up to defining these operators right here in terms of the position and momentum of the ladder operators. And there you go. So that's how you quantize the electromagnetic field. You will find, as always, the lecture notes with the derivation step by step.